Welcome everyone to back our class. Today I will introduce about the complex space. This is kind of the fourth lesson in the introduction to the quantum computing and programming course. Today, the last lessons, we already introduced about Euler. We already introduced about the complex number and the real number, and the complex plane. And today we will go to the next level, how we can use about the Euler formula, how we can use the complex vector to compute, or to represent the qubit space. That's kind of the basic the information in the quantum computing. Complex space, we have a kind of very special part like in a complex number, like we already we have a complex plane, and we can represent in the 2 dimensions, right? We have a 2 dimensions plane, something like this. A B I, A B. Okay, this kind of you're very familiar with this kind of complex plane. But what about if we extend the complex space is even to more, to more dimensions. So how we can draw in the complex complex plane? So this is kind of a very big question. If you see in the part, we have c square. C square. That's we expand the complex number c square. So we have 2 parts. We have this one is x1 something, this one is c2, right? So this x1 the value can become the real number. Yes, real number. So if we have the extend the dimension for complex number, it's very hard to represent in the 2 dimension plane. So now we need to find a way to represent this kind of value. So today the lesson we will focus how you can transfer between the complex space to the new form can represent in the 2 or 3 dimensions vector. Okay, over here we have vector. For example, we have one vector v equal to the vector space vector space v, and this one in a complex vector. Okay, vector space space. Okay, and we have a vector v when we include the 2 values alpha and beta, and this one we can represent the 2 element x0 and x1, the I, or x2 or 2 plus the x3 I, and this one is alpha. Actually this one alpha and this is beta. So now how we can calculate all the the multiply the value in this kind of space. For example, we have a CD, this kind of new the number in the complex the space, and how we can multiply this multiply this in the the value, the complex number with the complex vector. So how we can do that? So over here we have some kind of special. If you see over here, we need to multiply unit. This one is u. When we represent in the u vector u, cu and v. So when we multiply c, we need to multiply this kind of group, and you can represent in the represent in the complex. In the previous part, when you multiply 2 vector or the one complex number and with complex vector, you only need to multiply with kind of real. This real do not have this part, right? But now when we have in the vector space, the c square, we need to have a special this special part, and similar. So that means that this kind of value, you see this kind of formula, you need to carefully about this part. Okay, this is c, d is in c. That means we need to represent c and d in need to have 2 parts. The first is real, and the second part is complex number. Yeah. Okay. When we have this kind of format, and you can calculate very easy. You can multiply this one, yeah, and multiply this one. First, as the third part you can multiply this one, and the fourth part you can multiply this one. And after you multiply, and you can plus two value for this part and this part. For example, this one is 1, is 2, right? So you can plus 1 and 3, 1 and 3, 1 and 3. And the third one you can plus about 2 and 4. Yeah. So you can see this kind of we have this kind of the vector, the vector result when we include the 2 dimension. Okay, this 2 dimension. Remember, we original one we have a 2 dimension, something 2 dimension. So the result need to have a same, the same format, the same format. Yeah. And the vector space similar. We have we have the basis for the vector space 0, 1, 0, and 0, 1. But over here we have a special thing. Remember, this one, the basis is called 0 and 1. It's called a qubit. Okay, qubit. That is the basis representation in the quantum computing. Qubit. Okay. Qubit and the state for the 0 equal to the there's 1, 0, and the state 1 equal to the 1, 0, 1. So this kind of you need the qubit vector or vector space in the complex vector. Okay. And when you see this kind of notation, it's equal to the qubit. Okay, in the computing. Yeah, remember. Okay, that's good. Yeah, this is a notation for the quantum computation. Yes, I just mentioned qubit. Okay, qubit 1 or qubit 0. In the computing, in the traditional computer, you will see only we have state 1 or state 0, right? But now we have a more notation. Yeah, we have this qubit. Yeah, so remember. And in the when we can have a vector, vector space, for example vector v, we can represent in the 2 part. Yeah, we have this kind of qubit. We can this kind can represent a basis, very similar like a complex vector. We can represent and based on the basis and multiply with a kind of the value, this value alpha, beta, this kind of value in the vector space. Yeah. The more thing when we have a vector v, so the qubit, the qubit vector, the qubit vector have this special notation. You can see. Okay, remember when you see this kind of notation, that means equal to the qubit vector, and that's basis for the quantum computing. Yeah, and the qubit v, qubit vector v equal to the v1, v2, this kind of 2 element, and this kind of 2 element we need to represent in the complex vector. Yeah, complex x1 x0 x1 I and x2 plus x3 the I. And over here is important. V0 and V1 need to in this. Okay. If this one is R, so we do not have this part. We do not have this part. Okay. But this one is in the X. We need to have this one. Okay. Just remember. Okay, and this is a length of 2 vector, So the length of 2 vector, we have x1, yeah, we have a x0 square, x1 square, x2 square, x3 square equal to the 1. Yeah. So have some special. If the vector qubit v satisfies this condition, so it's called the qubit vector. So when the qubit vector satisfies this condition, it can be considered as a qubit vector, and we can use, you know, the Euler formula. Yeah, Euler formula. Remember about Euler, we already have a third lesson, how to convert between the complex number into the a complex vector to the next, you know, complex lane, and how to show the relationship between the complex number and we have an angle, right? So this one is how we define the, you know, qubit vector, vector v. Yeah. Okay, this is how we can calculate about the transform between the, you know, the qubit vector and to the, you know, to the Euler's formula form. So if you see this Euler, right? This Euler, this Euler. Formulation. Yes, this Euler formulation. So this third one is similar. We can convert to this one. Yeah, this Euler formulation. In previous lesson, we already mentioned about the, how we can use the Euler formulation to transfer. Yes, transfer between the you know, complex number to the new format. Yeah. And when we have a qubit vector, so we can you know, calculate the value to the, you know, the length of two vector in the qubit vector is equal to 1. Actually, in the future we will have a very special, because this one is equal to the length. Yeah, the length. Yes, the length. So every, you know, the qubit state will be running on this kind of the atom. Yeah. So we'll look more about in future about this part. Yeah. Okay, we have a special thing in this part. I hope you can remember. We have a qubit vector. So qubit vector over here we can use Euler. Yeah, Euler, and this guy in there is C, and we can Euler formula. Yeah, and this guy a basis for how you can transform between this kind of complex vector and to the, you know, the qubit vector. Qubit vector. This kind of complex, and this kind of to know how to transfer to the angle and represent in the complex, you know, qubit vector. Yeah. The last one, when you have a two vector in qubit, or we have a two qubit vector, how you can calculate the phase difference. Yeah, the phase difference. So this formula to tell you how you can calculate, you know, this phase difference. So you can base on these two values. Yeah. In previous one you can calculate x1, x2, x3. Yeah. So after you, yeah, you can calculate, we can have this kind of total value. Yeah. Okay. And the qubit vector. So now, yeah, this part after we have the final form. This final form. So you can see the difference between the, you know, the complex space, and we have this qubit vector. Yeah. So in this form we only have a 3 parameter. That means we can represent into 3 dimension, x, y, and z, right? In the future, that's equivalent to the sphere. Yeah. Okay, so in this lesson, I already tell you about the qubit vector. Yeah, qubit vector. And we have you know the Euler formula in qubit. And we have phase difference in a qubit factor. Yeah, I hope you remember these key points. Thank you, everyone.